This is lecture 6 in the mechanical vibrations course, and these are the items that we would like to discuss today. First of all, I'm going to talk about something called logarithmic decrement, which is extremely useful when it comes to estimating the damping ratio of a single degree of freedom system. And then once we go through that, we'll talk about an alternative way the damping occurs, and that is, as opposed to viscous damping, is called Coulomb damping. And that mainly comes because surface friction. And I'm also going to be talking about items 3 and 4, where the mass moment of inertia of an object is measured experimentally based on what we have developed so far in the course. And finally, talk about the stability of a system in the context of for example, an inverted pendulum. Okay? So, logarithmic decrement, whatever it is a process or a technique for estimating certain system parameters. And the most important one is zeta, okay, which is the damping ratio. And what we're going to do, first of all, let's say that some information has been recorded based on displacement as a function of time for an oscillating underdamped system. Okay, now, first of all, if it's underdamped, oscillating system, vibrating system, we know that zeta is going to be less than 1. We have discussed this thing about a week ago. And suppose you use an accelerometer to find the position of the point that you're making measurements at as a function of time, the displacement as a function of time. Okay? Out of that curve, we are going to estimate somehow this value of zeta. Okay, you'll see. First of all, if you have an underdamped system, the solution or the response of the system is given by that expression. This comes from 3 lectures, okay, where you had the mother of all equations, mx double dot plus cx dot plus kx equal to 0, or an alternative way of writing that down was dividing by m and transforming it into x double dot, so 1 times x double dot, plus 2 omega n zeta x dot, plus omega n squared x. This is the canonical form of that equation. But the solution to that, we said that it looks like this, okay? And the response, being underdamped, will be an oscillating system like that, where the amplitude is decreasing exponentially because of this guy e to the negative zeta omega nt. The amplitude is decreasing. That a is for example, maximum amplitude, all right? And there is omega d buried in there, which is related to omega n. And there is phase, okay? So, of course, part of our job later on is to find out what the phi is and what the a is, etc. Particularly when we do later on force response. But right now, this a and that phi, because it's a free vibration, is determined from initial conditions. And I had the expression for a and phi from a week ago, and it was terrible, but it's there. Once you have the initial velocity and initial position, you can find a, you can find phi. But at the end of the day, if you use an accelerometer, for example, to find the position versus time, you get a curve like this. Notice that this is a periodic, it has a period which is t. This repeats itself, and this t is related to omega d, not omega n. This is the period associated with damped frequency, omega d. And relationship between this t and omega d is, for example, t equal to 2 pi over omega d. Okay. Now let's move on. So suppose this first peak appears at T1 and the second peak appears at T2. Let's call this peak that we can actually look at the screen of our display coming from the accelerometer or attached to the accelerometer as x1 and x2. So delta, which is called logarithmic decrement, is defined to be the natural log of x1 over x2. This is just a definition. So logarithmic decrement delta is the natural log of two consecutive peaks. Now, it doesn't have to be x1, x2. It can be x2 and x3 or x3 and x4. It doesn't matter. Two consecutive peaks that I have here assumed to be at T1 and T2 or x1 and x2. Okay? Good. But just remember, any two consecutive peaks, we are referring it to at 1 and 2. Now, how do you find x1? Well, you go to that top equation, you plug in t equal to t1, and you get this long expression. And how do you get x2? You go to this expression up here, you set t equal to t2, and you get the thing down below it. First of all, notice that this a cancels that. We know that, okay? And these exponentials, notice, for example, I can say T2 is equal to T1 plus big T, right? T2 is equal to T1 plus big T. So I can go and replace this T2 right here in the denominator as the exponent as T1 plus big T. And the same thing now here. We have a T2 inside of the sign. We replace it with T1 plus big T. Okay. So when you do that, this is what you're going to get. Notice that T2 has been replaced with T1 plus big T, and the same thing down here. First of all, you can see that this actually simplifies very nicely because of the properties of logarithm. That thing on the top with the exponential completely cancels the thing in the bottom, except that this big T is going to be left over. Okay. So this cancels that, except in the denominator, you have e to the minus zeta omega n big T. Okay, so let's go to the next slide. See that? This is going to cancel that. And all I have done is to expand this thing. It was omega d times T1 plus T. I've multiplied it out. So written it as omega d T1 plus omega d big T. Okay, what do we know? First of all, by definition, big T is 2 pi over omega d. So big T times omega d is just 2 pi. See? Big T times omega d, which is right here, is just 2 pi. So that's going to be sine of something plus 2 pi. And we know from properties of sine of something plus 2 pi is the same as sine of that thing. Okay? All right. So that sign cancels the sign down here, because at the end of the day, this is the bottom is sine of omega dt1 plus phi plus 2 pi, but that doesn't do any damage. So this sign cancels that sign. They're exactly the same thing. And over here, I explained to you that zeta omega nt1, zeta omega nt1, those exponentials cancel each other out, but that big T is going to be left there. Now, from your high school algebra, you know that natural log of this, first of all, it is because it is e to the minus zeta omega n. So this thing, 1 over it, is e to the zeta omega n big T, right there. And properties of logarithm is that this guy comes in the front. So delta, logarithmic decrement, is equal to zeta omega nt. So just pay attention here. Look what happened. Delta we know because we measure. Big T we know because we are looking at the graph, the distance between two peaks, okay? And omega n we know in terms of big T. In other words, omega n, look at it, big T is 2 pi over omega d, that much we know. But omega d is related to omega n like that. Okay, so we know what omega n is. Out of that, see that? Omega n times t, here, omega n times t. Omega n times t is 2 pi over square root of 1 minus zeta squared. See that? We have omega n times big T here. And omega n times big T, just the product of this and this, is 2 pi over square root of 1 minus zeta squared. Right there. All right? So this thing, omega n times big T, we can replace it with 2 pi over square root of 1 minus zeta squared. There we are. That's it. We know delta because you're looking at the graph. We have two consecutive peaks on the screen. Take the natural log of the ratio of the two. We know delta. The only thing that we don't know in this expression is zeta. So you can solve for zeta. It's just basic algebra. Algebra, just algebra, right there. Square both sides so that you get rid of that square root. Solve for zeta squared, and then take the square root of it, and you get this. From here to here, straightforward algebra, and we know what delta is. So, if you look at your screen and you see that graph, you know what delta is. If you want to know what zeta is, plug it in there. And this is two consecutive peaks. It doesn't have to be the first two. It's just two consecutive peaks. Okay? Now, by the way, notice that if zeta is a small, actually, we can do a little bit of approximation. Just look at the expression on the left side. Right here, the very first expression on the left side. If zeta is a small, the zeta squared is even smaller. And 1 minus zeta squared is actually very close to 1. So you have delta equal to 2 pi zeta right there. And zeta, see that? Delta equal to approximately 2 pi times zeta. And you can solve for zeta, you get approximately delta over 2 pi. So for light damping, 2%, 3%, 4%, 5%, the estimate of the damping ratio is just logarithmic decrement divided by 2 pi. Very, as a first approximation. Now, as I mentioned, any two consecutive peaks could have been used. I just use x1 and x2 for illustration. And you can apply this not only to displacement, but you can apply it to velocity versus time or acceleration versus time. Doesn't matter. But Inman, when it comes to illustration, he has used displacement versus time. But this could have been velocity or it could have been acceleration. And but Inman uses displacement. Now, just one comment. If notice that in this particular problem, I am assuming when you take this sinusoidal, this decaying sinusoidal, okay, kind of the average of it is 0. Right there, you can see that. But if the average, if you drew this, for example, you look at your screen and the screen looked like this. What I mean is that it was hovering around an average value, a fixed value. This is hovering along x equal to 0, around x equal to 0. But if your plot was so that it was hovering along a different value, when you take this formula, this delta, do x1 not from here to here, you do it from peak to peak, okay? From peak to peak. So from here to here, here to here. Okay, so just be careful if your graph does not hover around 0 value. When it comes to x1, don't just like take the peak here. Just take the difference between this and that. So peak to peak is going to be this, right? This height. This height is peak to peak. This height is peak to peak. Okay, from here all the way to where the bottom point is. Okay, so just be careful. I know this may sound weird the way I explained it, but you just have to sit down and think about it. But if you have any questions, please let me know. Okay. Now, you might say, okay, could I have used maybe 10 of these peaks in order to come up with the answer instead of being 2 consecutive peaks? The answer is yes. Suppose you look at n peaks. Here, n plus 1 peaks, okay? Now, n of them. N oscillations, basically. If you define delta n to be a ln of not 2 consecutive one, the first one divided by the last one. So delta n is natural log, not x1 over x2. That's what it was before. Delta was x1 over x2. Now, delta n, let's take it to be x1 over xn plus 1, ln of it. Now, notice that you can rewrite that as x1 over x2, x2 over x3, etc. And these x2s cancel, the x3s cancel, and you get x1 over xn plus 1. You get exactly this. But you know from properties of logarithm, you can add these up. That's the property of logarithm. Okay? This thing, the ln of 2 consecutive peaks, isn't that what we call delta? Ln of 2 consecutive peaks, 2 and 3. That's delta. Ln of 2 consecutive peaks. This is delta. So I have n delta here. N delta. Okay. So you just look at this, all right? Just look at this. Delta, we already had an expression for it from the previous slide. I just plugged it in. Remember, delta was this. And I have an n in front of that. Okay. And you can solve for zeta squared out of this. Solve for zeta, that's not zeta squared, zeta, and you get that, right? So if you took n of these, and you took the ln of x1 over xn plus 1, that's this guy, you plug it in, you get maybe a better estimate for zeta, because you're relying on more data essentially here. And remember, this is by definition what delta n is right there. And if you just look at this equality, this, you see that? You see this? If you get delta, it's going to be 1 over n of that. The point is that if you use n pieces of data on the screen, this is what you can use. But you can use any 2 consecutive one, the n is 1, and this is what we call delta, and it's the same animal. There is another useful, very useful formula that I want to just mention that here. Let's take, for example, let's take this setup on the left side, for example. Displace that and let it go. So when you displace it, you move it by some amount. Let's hypothetically say you moved it by, I don't know, 10 millimeters, and you let it go. This begins to oscillate, and that 10 millimeter becomes smaller and smaller. At some point, it reaches 5 millimeters. So if you counted how many oscillations it took to reach half of the amplitude that you applied, we can use this formula to estimate zeta. Okay? So here's what I'm saying. In this problem, move this thing by some amount, 10 millimeters, whatever is possible, let it vibrate, and find out how many full cycle it took in order that for that 10 millimeter to come to half of it, which is 5 millimeters. If you have that number, plug it in here, and that gives you an estimate of zeta. In the case of a pendulum, same thing. Move this ball and let it go. If this angle, for example, you displace it just hypothetically by 20 degrees and let it go, find out how many complete cycles it took for that 10 or 20 degrees to reach 10 degrees, half of it, and just plug it in there. This is a very useful rule of thumb that one can use also. Okay, let's do an example. A problem. We have a free damped response. You can see that there's a damper there. The mass is 2 kilograms. Okay. And we estimated the stiffness. We estimated the stiffness of that spring to be 1500 Newton per meter. Okay. In other words, we apply a force. We found out how much this moved. You took the force divided by delta, or the amount that it moved. That's going to give you an estimate of your stiffness. That's what it means. Static deflection means you move this thing slowly by applying a certain force. When the force reaches maximum, find out what the maximum displacement is. The ratio of it will give you the stiffness of the spring. And that's a static deflection, basically. Now, suppose we got this curve. Suppose we did an experiment, we put an accelerometer and recorded the position of the mass as a function of time or some other gadget. I mean, you might say, well, accelerometer can measure acceleration and velocity and things like that. It can also display displacement, but there are other things that can be used to measure displacement, okay? And suppose this is the curve that we got, not drawn to scale. Obviously, experimental data is very, very zigzaggy and things like that. So this is the ideal and cleaned up version. So suppose, and it's not drawn to scale. Suppose at this time, the first peak, at some time, the first peak was 9 millimeter. The adjacent peak was 1 millimeter. Okay? So the logarithmic decrement is natural log of 9 over 1, right? 9 over 1. You use your calculator, you have your delta. You have the value of k, by the way, it's given to you. Plug delta in that expression that you have to know, memorize, write it down, I don't know. And then you got your delta, plug it in, and you get 0.33, which means 33% damping. That's a lot of damping, but anyway, that's what it is, okay? And if you want to, of course, this will give you critical damping, but if you want to know what the damping value of this damper is, what the C value is, you just have to go and plug it in the things that you know. C critical, remember, zeta is the ratio of C over C critical. If you know zeta, we got it. If you want to know C, well, you better write down what C critical is. C critical, this is one way of writing it, 2 square root of mk. Another way of writing this thing is 2 m omega n, same thing, okay? And you get your critical damping. Zeta itself is C over C critical, so C is zeta times C critical, plug it in, and this is your damper value, damper coefficient. There. Newton second per meter or kilogram per second. Okay. All right, so we did this problem. And now we're going to start the concept of Coulomb damping. I would like to introduce you the concept of Coulomb damping as opposed to what we have seen so far, which was called viscous damping. Now, this kind of a Coulomb damping is more appropriate for situations where you have a friction contact, surface to surface, or dry friction. And the problem is that as soon as you use Coulomb damping, the governing equation, the mother of all equation, becomes nonlinear. And it's not as simple as the case that we dealt with, where the equation was mx double dot plus cx dot plus kx equal to 0. So cx dot was because of the viscous damping model, but here we don't have that, and we have to handle the situation differently. So let me show you a free body diagram of a block that's sliding on a surface, for example. Now, I'm assuming that x pointing to the right is positive. In the case of Coulomb damping, the value of the friction and the direction of it depends on the velocity, on the sign of the velocity value, okay? And not the magnitude of it. Like, it is not a constant times x dot. What it does is the friction or the friction is constant, but changes according to the direction where the block is moving. For example, if the block is moving to the right, the friction is a constant and it points to the left, opposing the motion. So force of friction is negative mu n. So the reaction force, the ground reaction times the coefficient of friction. If the block is moving to the left, the friction points to the right, and the value of that friction is still friction coefficient times the normal reaction force, which is there. So essentially, fcx dot, in other words, the value of the friction is not a constant times cx dot. It changes according to the direction of the motion. Okay. There is a comment that I made here. Both of these blocks are assumed to be drawn to the right of the equilibrium position. And this is why some people may say, wait a minute, why is this kx not kx, the direction of it? Why is it like that? Now keep in mind that the value of x can be positive or negative because you're measuring from equilibrium position. On one side is positive, on the other side is negative. So in fact, this kx can be pointing in the other direction depending on where you are when you draw the free body diagram, to the left of the equilibrium position or to the right of it, because the sign of x, the algebraic sign of x, can be positive or negative. But anyway, let's not worry about that complication. You write down sum of all the forces equal to mass times acceleration, and you clean it up. Clean it up means this time keep mx double dot and kx on one side, take the friction, which is constant, to the other side. So we get this, and if it's moving to the right, and if it's moving to the left, left is exactly the same thing, except that this minus becomes a plus. Okay. Incidentally, the value of mu is the kinetic coefficient of friction. Remember, from elementary statics, you have two types of friction coefficient, static and kinetic, and this is the kinetic one that we're talking about. If you look at some of these elementary books, you do find a friction coefficient, both static and kinetic, for different scenarios, such as here. This is coming from Inman's book. Metal to metal lubricated, the kinetic coefficient is 0.07, static is 0.09. It's always the case that the kinetic is bigger than the static. For steel on steel, metal on metal on metal, unlubricated, it's a lot higher, 0.3 versus 0.75. And of course, there's wood here and rubber on steel. It's going to be a lot of friction, and it's going to be 1 and 1.2 for that situation. Now, we are lucky because these two equations, although the entire thing is a nonlinear equation because the right-hand side changes depending on how the block is moving, but individually they can be solved. And if you say how, this is a non-homogeneous equation. The solution to it is a particular solution, which is just a constant, namely constant means mx double dot goes away, and you solve for x, that's the constant value. Same thing down here. So in one case, it's going to be minus mu mg over k, and in the other case, it's going to be mu mg over k. And that is the particular solution. You have to add to it the homogeneous solution. Homogeneous solution means set this thing equal to 0, the right hand side equal to 0, and we know what the solution is. It's a constant sine omega nt plus another constant cosine of omega nt. And those constants are determined by initial condition. So now let me go ahead and show you what we have. If we assume that the block is displaced and released from the rest condition. So if the initial velocity is 0, you can see that, for example, that in that case, sine will disappear, will not be there, but cosine will be there. Okay, so there we are, right there. For example, if you move the block to the right by the amount x naught and released it, the solution to that equation is going to be right here. All right. For the until see, you have to keep in mind that until it goes all the way to the end and then goes back. So basically, it's made of two pieces: the first cycle and the second cycle. Okay. So what do I mean by that? Let's go to this. Just remember, this is releasing from zero initial velocity. So here's the situation. In the first half cycle, it's right here. This is going to be one of the equations that I wrote on the other page. And when it goes to the second half cycle, okay, the equation changes and it is what you saw on the previous page. See that? Let's go back. This is the first half cycle. This is the second half cycle. They're not the same. That's why this curve and that curve, their formulas are different, and then it repeats itself. There are some observations that I would like to make. First of all, notice that when time is 0, initial position of the block is x naught, right there. And then x naught, and then x gets smaller and smaller and smaller because it's moving to the left to reach its equilibrium condition. So notice that if you drew those curves, the two previous curves, over many cycles, this amplitude decays, but not exponentially. In the case of viscous damping, this was going exponentially down. But in the case of Coulomb damping, it is linearly decaying. You can see that. That's a characteristic of Coulomb damping. Now, in Coulomb damping, after a while, actually the block stops, literally stops, if you go with that model. Okay? Whereas in the case of viscous damping, it never stops. It approaches the 0 position, the equilibrium position, exponentially or after infinite length of time. Okay? But in the case of Coulomb damping, after a while, actually it stops because spring force is not big enough to overcome the friction force. Okay. The frequency of oscillation. This is an oscillation. The frequency of this oscillation is depend on omega n, not something called omega d. Remember, let me go back for a second. We have omega n here. Omega n. All right. So that's what this is saying. In the case of viscous damping, the frequency of oscillation, which was exponentially dying, was actually omega d. Now, omega d, damped natural frequency, was related to omega n by taking it and multiplying it by 1 square root of 1 minus I squared. Okay. Now, in real life, the situation is neither completely viscous or completely Coulomb. Coulomb damping, the real life problem is something in between these two, and we're going to introduce material damping later on, which happens to be a compromise between both situations. Okay. One last thing, notice that in every half cycle, see that? For example, in this half cycle, the amplitude went from that guy, x naught, to x naught minus 2 mu over k. You go from this to the next half cycle, once again, that is reduced by another 2 mu over n. That's why it looks like that. So for each half cycle, the amplitude drops by that much, and because of this decay is linear. All right, a few more things. Let me remind you once again that the frequency of oscillation is omega n, not omega d. And the slope of this line is very easy to work it out. It's just that expression. All you have to do is take, for example, x naught minus that and divide it by time, for example, and you're going to get some expression. The slope of the envelope line, this is the envelope line, is that expression. Now, for each cycle, it drops by 4 mu over k. For each half cycle, it drops by 2 mu n over k, which is what I said in the previous slide. Now, the motion stops if the spring force, which is k times x of t, see, k times x is the spring force. If the spring force is less than the friction force, then it's not going to move. Okay? So this is when the stopping takes place, and what we can do is we can find out after how many cycles, for example, this thing drops below mu n over k, because xn, if we go n cycles, for each cycle x naught drops by that much. See that? For mu n, big N over k, after n cycle it drops by that much. You start with x naught, drops that by that much, and if this number is less than mu n over k, we know that the thing stops. So we can figure out actually what n is, okay? So based on this equation, see that? This equation, we can solve for n, and we get that threshold value. So let me see, right there. So n equal to this, or slightly bigger than it, in that many cycles it stops. Let's do an example. Let's do an example which involves real numbers here. Suppose that we had a block which was sitting on a surface attached to a spring, and I displaced the block by 30 millimeters and then let it go. Now this block starts oscillating back and forth, and because of the friction between the two surfaces, it slows down. And the most reasonable thing to do, at least deciding between viscous damping and Coulomb damping, this is a contact problem, so Coulomb damping is more appropriate. And let's say that we measure the displacement of the block as a function of time, and we notice that actually it looks like this. Notice that the amplitude of the block is decaying in a more or less linear fashion. Therefore, that's another indication that Coulomb damping is more appropriate. Let's say in 1 second, it did 4 oscillations, and it went from 30 millimeter that we initially moved it to 3.5 millimeter. So 4 cycles in 1 second. What we want to know is what is the friction coefficient, and all of that mu. First of all, this 4 cycles in 1 second is the frequency, but in hertz. So if you want to get the frequency in radians per second, you take the 4, you multiply it by 2 pi, and you're going to get the value of this thing in 25.13 in rad per second. Now, we know what the slope of this line is. You go to the previous slide, but first of all, you can see that the slope of this line, change in height divided by change in horizontal distance, which is going to be it's dropping, right? It is dropping, so it goes from For example, 3.5 minus 30 divided 1 second, the slope of this line is 26.5 with a negative sign, because you can see that it's a negative slope. So 3.5 minus 30 divided by 1 second, that's it. But we also have an expression for the slope in terms of the stuff that we did derivation a few minutes ago. There is a friction coefficient that we don't know. There is the gravity constant, and there is omega n. So we know everything in this equation. We know everything except for mu. You solve for mu, and you're going to get 0.107. So this is a well lubricated surface, actually. If, for example, we assume that the block was made out of steel on a relatively rough. So another problem here, we have a 2 kilogram mass that is attached to a spring, and it's on a surface, and we know that the surface exerts a friction force of 3 Newton on it. What we want to know is what is the coefficient of friction. First of all, we know the relationship between friction force and the weight of the object. So the weight of the object times mu is equal to the friction force. Okay, so mg, which is the weight of the block, times mu is equal to friction force. So you can find the friction force directly by taking the force of friction and dividing it by the mg, and you're going to get 0.153. It says after how, and then part B says after how many cycles does the amplitude decrease by 20 centimeters. Okay, so if you go here, we have this expression which gives you the amplitude after n cycles, okay, after n full cycles. So we start with amplitude of x naught, whatever it happens to be. After n cycles, each cycle reduces by that much. So this is what you get. Now, if you take x naught to the other side, you have this thing you're told is 20. In other words, final amplitude minus the initial amplitude, 20. And in this expression, we have mu, we have n, and we have k, and we're going to get n out of it. Approximately 7, after approximately 7 full cycles. Okay? One more problem. We have a 5 kilogram mass attached to spring of a given stiffness, is sliding on a rough surface, and we have the coefficient of friction. Okay, it says find the number of cycles for which 50% reduction of amplitude takes place. Okay, so it says it goes from whatever it was, for example, x naught, to half of x naught. Essentially, that's what it's saying. So suppose that they assume that the block is initially positioned at 5 centimeter or 0.05 meter from the equilibrium position. Okay, let's go ahead and find out what we have. This is the expression which tells you what the amplitude is after n cycles. Okay, what do we know? We started with 0.05 amplitude, so x naught is 0.05 meter, and we want to go down to half of it, 50% of it. So half of 0.05 is here. You just plug everything else in here, you know everything except n. And that will give you the n equal to 6.25 cycles, approximately six full cycles. And then it takes after how long it will actually does this thing. So first of all, we know the natural frequency, because after all, I have to take that many cycles, multiply it by the period of each cycle, right? Okay, so we need the natural frequency. Square root of k over m. You have everything here. You have omega n 9.9 rad per second. And period is 2 pi over omega n. Okay. All right, 2 pi over omega n. You just plug in, and you get the period is 0.634 second, and each one of these cycles takes that much. So you multiply 6.25, 0.634, and you're going to get the answer. So it takes about 3.96, almost 4 seconds for the amplitude to go down to half of what it was. All right. Okay, based on the material that we have covered in the past 3 weeks, I want to talk about a measuring instrument which allows us to find the mass moment of inertia of a three-dimensional object about an axis that passes through the mass center of that object. Okay? This is done through what is called a tri-filler suspension device. So, as an illustration, I show you something here which is identical essential mechanisms. On the left-hand side, it's the old-fashioned one when there's a tray that's suspended through three wires. And on the right-hand side, essentially it's the same thing except that instead of putting the object that you want to measure something about on the tray, you suspend it, and then we don't have a disc. It has something that you see there with three arms. Okay. Now, this is called tri-filler suspension device. And the object that we want to measure something about is what you see here shown as this block. It doesn't have to be a block. It can be any shape. But you have to know where its mass center is, okay? And there are other ways of finding mass center of an object. So what you do is you place this object on that tray so that its mass center sits directly above the center of this device. Based on the response of this pendulum, and what do we mean? What do I mean by this pendulum? You twist this tray and let it go. It starts oscillating back and forth with a certain frequency. So, based on information that comes from that frequency or period, we're going to find what is the mass moment of inertia about the axis that passes through the mass center and in the vertical direction. Okay. Now, I've found many references on YouTube where this is illustrated. So the tray is shown here on the left side without anything placed on it. If you twist it and let it go, it starts oscillating back and forth. And here is the same gadget that I showed to the right of that, a more modern version of it, but it does essentially the same thing. Okay, so what's the story? Here we have the wires shown, and this disc, this tray, is slightly or turned by an angle theta, as you can see here. Obviously, the rope, the wires are going to get stretched, and they actually also move from, for example, this wire from that location to this location. And there's an angle here, but this angle alpha is not the same as angle theta. We'll see that. Okay, so let's see now. What do we have here? L is the length of the wire. Okay, we are assuming that basically this doesn't stretch that much. Okay, and then R naught is the radius of the disk. I naught is the mass moment of inertia of the disk. There's the disk, and we know what I naught is. It's 1/2 r naught squared. We know that from elementary deformable bodies. The mass of the disk, the mass of this is m naught. The mass of the 3D object is m. G is the gravitational constant. T is the period of vibration of this. In other words, when you twist this thing, having placed the object that you want to measure something about with its mass center directly above the center, it will oscillate with this period. And what we want to know is the I, which is the mass moment of inertia of this thing that we want to measure about its mass center in the vertical direction. So the axis that you want to measure something about is the vertical direction through the mass center of this object. Okay. I'm going to show you that based on the information provided, the I is going to be calculated according to this expression. Notice that we have the period here. In other words, you have to do this experiment, and you have to see what is the period of oscillation of this disk with the object placed on it. And then once you have it, everything else you know, you plug it in here and you get your eye. Okay? Obviously, we are assuming everything small angle, so you just have to be careful. Okay, where is that thing coming from? It is by no means obvious why that should be our answer. So what we're going to do is a few things. First of all, when the wire displaces, more or less the force in this wire is 1/3 of the mass or the weight of the disk plus the weight of the object that we place on it. Why is it 1/3? Because there's 3 wires here. Okay, so there is the force or the tension in that wire. Now, this angle alpha, if we take this dashed line parallel to this wire hanging original configuration, the component of this wire force in the tangential direction is just this number, this tension, times sine of alpha. So that's going to give you this. But if alpha is small, sine of alpha and alpha are the same. So it's going to be just the tension times alpha. So the component that causes this whole thing, tray, to twist, component of the force that creates a moment and causes this thing to twist, is right here. Okay? And keep in mind that there are 3 of these for each of the wires. First of all, if you look at this arc, let's concentrate on this particular wire, the one on the left. In this right triangle, that arc or that side is approximately L times alpha. And how do we know that? It's actually very close to L sine of alpha, but angles are small. So L alpha is on one hand this length. But you can also take this triangle sitting in the plane of the tray, which is that length is R0, the length of the disk or the radius of the disk times the angle theta. So I know what alpha is in terms of theta, and I'm going to write everything in terms of theta. Okay. And how do we do that? This is the sum. There's something missing here on the left side. This is sum of all the moments. Sum of all the moments about the center. And I'm really sorry. This should be sum of all the moments about the mass center is I of the whole thing. That means the gadget that we want to get something, to know something about, and the disk in the vertical direction, theta double dot. Okay. So let's see. Remember, what I left out here, unfortunately, is sum of all the moment about the mass center. And where are these moments coming from? Well, it's coming from these tangential component of the tension. So there is one over here in the plane of the disk. There's one over here in the plane of the disk, and another one over there. And there's 3 of them. Okay, 3 of them. So you take the moments about that. The moment arm is R0 in each case. Okay, the moment arm is R0, and multiply it by this fellow. And there's 3 of them. So that is the moment, as you're seeing here. Okay, equal to I of this whole tray plus the I of the thing sitting in it, I plus I naught times theta double dot. Okay. Good. But we know how to get rid of alpha right from this equation. You know how to get rid of alpha. So alpha is gone in favor of theta. And here is the mother of all equations for that pendulum, written in detail here. Here is the effective mass. Here is the effective stiffness. And the natural frequency of oscillation of this thing is the square root of effective stiffness, effective K, divided by the effective mass. Right there. And if we know omega n, we can find the period. You just write down the expression for omega n, 2 pi over t. And if you plug it in here and you square both sides so that you get rid of the square root, you're going to get that expression in terms of the stuff that's here to be like so. And this is a single equation in terms of big I that you can solve for, right? That's what we want. We want this I, isn't it? We want this I. And we're going to get, there we are. Just algebra. So if you measure T, and you can do that with a stopwatch, something like that, you know the mass of the disk, the mass of the object that you want to know something about. This I naught, as I said, is 1/2 of the mass of the disk, which is m naught, times the radius of the disk square. L is the length of the rope or the wire, and G is the gravitational constant. You get your I. Okay. The last subject that we want to discuss in today's lecture is the concept of stability. It's 3 weeks now we have looked at this equation, which is the mother of all equations, single degree of freedom, small oscillations, obviously, small oscillations, and with damping. Okay. Now, when we solve this, if there is no damping, this is going to be strictly oscillating forever. If there is a damping, such as what we have here, viscous damping, the oscillation amplitude is going to die down. And eventually, after infinite passage of time, it will reach zero. So essentially, it will never go to zero, it approaches zero. And every single case that we have looked at, except for one that we did on I think it was on Tuesday, these coefficients, physical parameters, M, C, K, they were all positive numbers. And remember, we run into several possibilities. This can be, of course, if it's undamped, there is no C here. Overdamped means that the damping ratio, which comes from these parameters, damping ratio zeta, is damping C divided by 2 square root of Km. Remember that? If that damping ratio is bigger than 1, it's an overdamped situation. The solution dies down without oscillating. If it's equal to 1, it's critically damped. Again, it dies down without oscillating. But if it's less than 1, we get an underdamped situation where the amplitude decays exponentially and the solution looks like that. But the point is that the solution always stays bounded, right? Always stays bounded. As time goes on, the solution always remains below, below a certain value, basically in a band. You can see that in a band, stays there. Okay. And of course, in the undamped case, this oscillates forever, never dies down, etc. Now, what happens if one of those coefficients or more than one of them happen to be negative? Well, you might say, wait a minute, mass is not going to be negative, K is not going to be negative, and neither is C. You're right. But that mx double dot plus cx dot plus kx is only for a mass spring damper system. We have a lot of other situations where it was a single degree of freedom and we had to reduce it to that kind of an equation. So we got an m effective x double dot plus c effective x dot plus k effective x. And those things we don't know. And we saw one case where something actually there could become zero or even negative. Not that much, Yeah, that's true. We did on Tuesday. So the moral of the story is that if as time goes on, the displacement grows unboundedly, grows and never stays within a certain range, grows unboundedly, this is what we have called divergent instability. Okay. Another situation is flutter instability, that the solution oscillates and it grows unboundedly. Please look. Some of you may go back to your recollection of how we started the course 3 weeks ago, and remember, I may have shown you the Tacoma Narrows Bridge video. And I told you that the oscillations of the deck grew bigger and bigger and bigger, etc. Yeah? You might say, okay, well, so isn't that flutter instability? Haven't we already seen that? The problem is that that particular video that I showed you, there was a forced vibration. What we're talking about here is free vibration. Can we have instability in free vibration? In the case of Tacoma Narrows Bridge, the one theory is that the wind flow over the deck caused this harmonic forcing, okay? This periodic force, and the frequency of that forcing happened to match some natural frequency of the structure. That's not what we are talking about here. We don't have any external force, okay? As we will see that as the example that I'm going to do for you, we don't have a harmonic response or a forced response to talk about the resonance. This is not the same thing that we're talking about. Okay, that stuff comes in week 4 and 5, okay? Harmonic or force response. But that's not what we're talking about right now. Let's look at this example. You have seen this. Exactly the same problem we saw it last week. Actually, on Tuesday, not last week. The only difference was that I didn't draw 2 springs for you here. I just drew 1 spring. But this is the same thing, okay? Essentially, we have same kind of an animal. It is an inverted pendulum. If the mass was below, if this thing was on top, so that this was actually hanging from the ceiling, there won't be any instability. But you will see that there is an issue with this inverted pendulum. What we did on Tuesday was to say, okay, let us draw the free body diagram associated with the structure. Okay? First of all, there is the weight. Okay, if this displaces point the amount theta, there is the weight of that ball. There is a force in the spring on both of them. They add up because these are in parallel. That's 2 of them. 2 times the amount of the stretching or compression of each each of these springs, which actually is L over 2 in that right triangle. See that if this thing goes by the amount, theta, if this vertical line tilts by the amount theta, for example, that length, the length here, which is L over 2 times sine of theta, this is the angle theta, sine of theta will be giving you the stretching or the compression. But if theta is small, sine of theta is approximately theta, and we're going to approximate that in a second, in a few seconds, by approximately theta. And of course, there is a force due to the reaction here, but that's fine. We're going to take all the moments about this point. And that means we don't have to know what Fp is, because we take the moment about this point, and the moment of Fp about this point is 0. Okay? There we are. So, sum of all the forces, sum of all the moments about this point equal to mass moment of inertia. I'm assuming this rod is massless, so the mass moment of inertia about that point is just m times L squared. That's this term. So mL squared equal to sum of all the moments. And I've taken the moment and brought them all on one side. The moment arms, we just, we can just look at it and figure out what it is. For example, the moment arm of this mg is just L sine of theta. There we are. And I'm doing, for example, in this expression, I'm assuming that everything is taken clockwise, all the angles, sum of all the moment in the, let's see now, in the clockwise direction. So this has a moment clockwise about that point. The moment arm is L sine of theta. Okay, right there, L sine of theta. Mg is on the right-hand side. When it comes to the left-hand side, it becomes negative. Okay, and the spring force has a counterclockwise moment about there. So we have the force, which was written for you, is right here. KL sine theta. KL sine theta is actually the force, the 2 and 2 cancels here. And the moment r about this point is this vertical side, which is L over 2. This is L over 2 times cosine of theta. There we are. And it was on the right-hand side and a negative. When we bring everything to the left-hand side, that's why this became positive, this became negative. Look, sum of all the moment about this point in the clockwise direction equal to mL squared theta double dot. I'm measuring theta like that. Now, for small angles, sine of theta is approximately theta. Cosine of theta is approximately 1. And of course, again, sine of theta is approximately theta. Clean them up. There we are. I don't even have a damper here. You can see that. There we are. Effective mass, 2 ml. Effective stiffness, KL minus 2 mg. That's where the problem is. This is no longer positive for a certain combination of KL, M, and G. This may become 0. And if it may become 0, this is an unstable situation. And let me give you an example. If K is a very, very, very soft spring, as soon as this thing tilts, then it goes forever. It falls down, either on the left or on the right. And of course, in the worst case scenario, when K is 0, there is no spring here. Well, this is an unstable configuration anyway. So you can see what instability means in the context of the course that you're teaching, or you're teaching at this level. And I did it in the form of an inverted pendulum. We did this thing on Tuesday, and we are doing it for the second time today. So that's what the inverted pendulum is, and it's an unstable setup. All right, folks. So that takes care of the lecture. See you on Tuesday.